For the first time, NASA has touched the surface of Asteroid Bennu to collect the agency's first ever asteroid sample, which will one day shed new insights on the history of our solar system. So what's next? I'm your host, Lauren Ward, and hello. If you haven't heard, we made history yesterday. So let's bring you up to speed. At 6:12 p.m. Eastern Time, NASA attempted to collect a sample from a near-Earth asteroid named Bennu. Since arriving at Bennu in 2018, our OSIRIS-REx spacecraft has been orbiting the asteroid, mapping it, and studying it closely. And yesterday, the spacecraft descended on an asteroid surface, and its robotic arm touched down for a few seconds to collect the sample of an asteroid's rock and dust. This precious rock and dust that the spacecraft will safely enclose in a capsule could tell us more about the history of our solar system. And that's why in 2023, the sample will have made its way back to Earth so we can study it. So the question is, what happens next? Today we are joined by three experts: Danny Dell'Agostina, OSIRIS-REx lead image processing scientist at University of Arizona, Jason DeWorkin, OSIRIS-REx project scientist at NASA Goddard, and Bo Bierhaus, OSIRIS-REx TAG-SAM scientist at Lockheed Martin. Thank you so much for joining us, you guys. It has been a wild 24 hours.
Thanks, Lauren.
Great to be here. Thank you.
We're so excited to have you. So, Danny, let's get into it. I understand there's a new video taken by the spacecraft as it actually descended to the surface of asteroid Bennu. Could you walk us through how that was even created?
Sure, Lauren. So this is a video created from SamCam images, and SamCam is one of three cameras that was built by the University of Arizona specifically to acquire scientific data of asteroid Bennu. So what we see in the video is the TAG-SAM arm. It's extended out, and TAG-SAM is observing it as the spacecraft translates across the surface of Bennu, arriving at Nightingale, the sample site. And then you see, right as we make contact with the surface and our nitrogen gas bottle fires to collect that sample, there's a huge spray of material that's just lofted from the surface of Bennu. And this is a great sign. It looks like we picked up a lot of material, and that means that some of it likely made it into that sampling mechanism. So we are really happy to see this result, and the movie from SamCam is quite promising.
That is amazing. And it's so astonishing that your team was actually able to put it together so quickly. For our viewers at home, these guys have been up all night. So, Bo, your team will use this video to assess the response of TAG-SAM head to the surface. Could you walk us through exactly what we're seeing in this amazing video?
Absolutely. So the first part of the video, you'll see the TAG-SAM head centered in the SamCam image as Dan was saying. And as the spacecraft descends towards the surface at a leisurely 10 centimeters per second, about 15 times slower than walking speed, eventually the spacecraft senses contact with the surface. We sense contact with an accelerometer on board, and that told the spacecraft to fire the gas bottle, which then released gas under the released nitrogen gas under the TAG-SAM head, which mobilized material, we hope, into the TAG-SAM head as well as outside the TAG-SAM head. The two things that we're really examining in detail now that we have these incredible images is the response of the TAG-SAM head to the surface and the response of the surface to the TAG-SAM head itself. So of course, the surface is very interesting and very dynamic, and that tells us that the material is probably very weak and doesn't have a lot of cohesion, and so therefore is easily mobilized and potentially easily collected inside the TAG-SAM head. The second piece of information we're trying to understand is the geometry of the TAG-SAM head against the surface. So we want to know whether it was tilted or flush when it fired the gas. Preliminary signs suggest that it had a minor tilt at most, which is very good for sample collection. There's a great image now. You're seeing a pair of images of just before contact and just after contact. And you can see the TAG-SAM head tilting just a little bit. And in fact, you can see surface material moving in response to the contact of the TAG-SAM head. And we thought that this might happen based on some of the experiments that we had done with reduced gravity flight. And the final thing that we're doing is we're assessing the arm in the images as we back away, just to make sure that there was no damage to the arm. And so far, that all looks great too.
Absolutely spectacular. It is so interesting to watch OSIRIS-REx descend on the surface, to the surface of the asteroid Bennu, especially when you consider that these images are coming from over 2 million miles away. So fantastic. Jason, the team will analyze the sample once it's delivered to Earth, but before then, there is still a ton that has to happen. Can you explain how the sample will be handled from now until it lands on Earth?
Absolutely. So the next step is to take images of the material inside the sample head, inside of the TAG-SAM head. This weekend, we'll be taking measurements of the mass of the material by extending the TAG-SAM arm and rotating the spacecraft slowly around and measuring the change in moment of inertia. After that, we will assess whether or not we think we have enough material, and then if we do, we'll be opening up the sample return capsule and stowing the material inside. At which time we cut off the sample head, close up the sample return canister. You can see happening right here. Then in March, the spacecraft departs orbits around from Bennu, and then heads to Earth. The sample return capsule is jettisoned from the spacecraft, landing in the Utah desert at the Utah Test and Training Range outside Salt Lake City, the morning of September 24th, 2023. The spacecraft diverts, goes into orbit around the sun, and the sample return capsule is collected by the team of scientists and engineers and brought to a clean room in the Utah Test and Training Range to make sure that the pyros and batteries are disarmed, flown to Houston, to Johnson Space Center, where the curation team will open it up and then distribute the samples to laboratories around the world, including my own, to study the sample for decades to come.
That is fantastic. And I want to rectify something I said before. It's not 2 million miles, it's 200 million miles away. That is so much farther and more impressive than 2 million miles. So I understand that Bennu was far more rocky than we expected, making yesterday's maneuver more difficult than we had ever imagined. One thing that I think everybody is wondering is, was that experience watching Bennu, do the tag, was that nerve-wracking? And I really want to hear from everybody, starting with Jason.
So I've been anticipating this moment since 2004 when I started working on the predecessor to the OSIRIS-REx mission, OSIRIS. It's been an amazing journey, a lot of really talented scientists, engineers, managers, technicians, admins. It's been an incredible journey, and that these few seconds mean so much, and that the sample will be distributed as a legacy of this team that the world can enjoy, that scientists not yet born using instrumentation not yet invented can answer questions that we don't know how to ask yet.
Wow, what an amazing gift for the entire world. Danny, I'd love to get your thoughts too.
Yeah, well, so I got my start on OSIRIS-REx, also on the precursor to the mission named OSIRIS, as an undergraduate student in the early 2000s. And as we were leading up to this event, it occurred to me that I've been waiting my life to gather a sample. So I went into the event with a lot of cautious optimism, because this team is exceptional. And I know we had done everything possible to minimize the risks associated with gathering the sample from Bennu. Even though you mentioned, Lauren, it was more challenging than we were expecting. The surface was far rockier than anticipated when we designed the mission. So I felt confident that we had done everything in our control to achieve mission success, and the rest was up to Bennu. And it turns out Bennu complied, and it looks like we've achieved what we were hoping for, but there's a little more work to go to verify the amount of sample we collected.
Bennu definitely did an outstanding job, and it did exactly what we intended. Bo, what were you thinking during the tag event?
I was thinking a lot of things, so many things that it's probably hard to put in a small number of words in a short period of time. Of course, incredibly excited. Been waiting for this moment also since 2004. I started working on the mission in 2004. Have done 890 collection tests with TAG-SAM, multiple reduced gravity flights, and the team was incredibly well prepared. We couldn't have done anything more. We had rehearsed the tag twice before in real life with the spacecraft around Bennu, and many, many times before in simulations on our computers. So we had a pretty good idea of what to expect and what could go wrong and how to handle things that they might have gone wrong. The one thing we had not tested was the actual TAG-SAM collection event at Bennu. So even though we have done hundreds of tests on the ground and on reduced gravity flights, we had never done this sample collection event at Bennu before. So that was the last piece we hadn't done. It's an important piece, but as Danny said, fortunately, Bennu complied. It's one of the few ways in which Bennu actually worked in our favor. It was rockier than expected. There were particles being ejected off the surface that we didn't expect. But in this particular case, Bennu seems to have fallen in our favor. And after having worked 16 years on this program, to have all of that time collapse down into just a few seconds, it's a weird, surreal juxtaposition of timescales. But I'm incredibly happy and proud and excited for everybody involved.
Well, this team is second to none, and you guys were adaptable beyond any imaginable scope. So it's worth being extremely proud about. So we've been able to study asteroids that have come through Earth's atmosphere before. Danny, what is different about this sample in particular?
Now, that's a really good question, Lauren. So you're right. We do have meteorites that come from asteroids in our sample collections on Earth. But you know, those meteorites only represent the material that is strong enough to survive what is a very warm entry through Earth's atmosphere, as well as an impact on the Earth's surface. And so the data that we've obtained so far from Bennu using the OSIRIS-REx spacecraft, it indicates that the asteroid has water-bearing minerals and organic molecules. And this material might be pretty fragile, and thus it wouldn't be represented in our meteorite collection. You know, it likely wouldn't survive that atmospheric entry onto Earth's surface. But additionally, by going to Bennu to acquire a sample directly from its surface in a very controlled way, putting it in a safe and clean sample return capsule, we know that that material, it's not going to be contaminated by, you know, the Earth's surface in the same way that meteorites are. And so it really offers an unprecedented opportunity to study material from an asteroid that we might not have in our meteorite collection, and that is pristine and hasn't experienced contamination.
Fantastic. Okay, so let's get down to it. The internet is buzzing with excitement around yesterday's events, and many people have questions. So let's take a few now. If you're watching this and you have questions, submit them online by using the hashtag #ToBennu&back, or comment on the stream wherever you're watching this. Okay, our first question is from Anna2, who is an 8th grader at Mesa Verde Middle School, and she asks, is there a possibility that this sample can change the design of future bots made for the same purpose? That is an engineer in the making. Does anyone have a good answer for that?
We can try to answer that question. It is an excellent question, and we hope the answer is absolutely yes. One of the major challenges we had for this mission was trying to design a sample collection device for material that we didn't know what it was like. We didn't know what the mechanical properties might be. We didn't have a good understanding of what really the size distribution of the particles might be, and by that I mean how many there are of any particular size. We didn't know if the material was strong or weak. And now that we've done this sample collection event at Bennu, all of the data that we've collected, both during this tag event now, but as well as examining the sample itself when it comes back to Earth, we'll actually be able to make direct measurements of the strength of this material. How electrically conductive is this material? How magnetic is it? And these will inform ways that we can design systems in the future to interact with other asteroids for future missions. So absolutely, the answer is yes. It's a great question.
So speaking of material, Molly on Twitch asks, why did the rocks on Bennu crumble so easily? Are they very loose, or was there an impact? Was it because of the impact of the TAGSAM head being very forceful?
Danny, you talked about that a little bit.
Sure. Yeah, I can explain that. So, all of the indications that we had from the instruments on board the OSIRIS-REx spacecraft were telling us that boulders on Bennu are exceptionally weak. So even though the surface looks really rocky and jagged, we think that these boulders are almost like balls of mud and likely crumble very, very easily under even small forces. So while we weren't necessarily expecting the TAGSAM head to crumble rocks on the surface of Bennu when it was designed, we think that might be what took place during the sampling event.
Wow, yeah, I had that question too. That is a lot of debris, it looks like, but all very safe. So Joe on Twitter asks, will the spin to measure the mass collected cause a loss of material collected?
So the spin is very slow. Actually, Bowie, looks like you're about to say something. You're more expert than I am.
Want to take it? Sure. Okay. Yeah. Jason's making an excellent point. So the spin is very, very slow. It's a very gentle movement, and the way that the collection device is designed is there's actually basically a flap that prevents material from leaving the collection device after it's been sampled. So the material can go in when we collect it, but it can't come out after it's inside the sample container.
Okay, there you have it. Okay, so Nathaniel on Twitter asks, it was mentioned that there was a possible carbonate, that there's possibly carbonate on Bennu. If this is the case, is there any hypothesis on how the carbonate was formed? Any papers describing that?
Sure, I can answer that. Yeah, so there's actually a paper that just recently came out by our colleague Hannah Kaplan, who is a scientist on the team, who analyzed the composition of these carbonates. And so I would encourage you to check out her publication. But our leading hypothesis for how these carbonates formed on Bennu's parent body actually is that there was a large-scale hydrothermal system. So there was water flowing in the interior of the asteroid that percolated through cracks in rocks and eventually precipitated carbonate. And this is really exciting because it indicates that Bennu's parent body was a water world. And so Bennu is what we call a rubble pile asteroid, and we think it accumulated from the fragments of a giant impact on its parent body. And so by studying Bennu, we start to get pieces and clues about what took place on this water world in the early solar system before it was catastrophically disrupted.
And speaking of that, JL on Periscope asks, did you find any fault lines during your scan, or is this asteroid pretty much solid?
Jason, do you want to get that?
Well, I was going to say this is Bo's expertise, but I can answer for him. So there are lineaments, there are lines that run around Bennu in some spots. but there's macroporosity. There are holes, empty spaces inside Bennu based on the gravity model that we've developed from watching those particles fly around Bennu and from our close observations. So it is not a solid rock. It's very fluffy, and that's also consistent with the crumbliness of the surface that we saw.
So it looks like we have a lot of people really interested on how they can see these photos eventually. Dutch Steam Machine on YouTube asks, I would love to enhance and look at these photos once they arrive. Is there a website to download the raw photos as soon as they are received?
Yeah, so I can get this question as the image processing lead for the mission. So many of the images that were recently acquired for the sampling event itself are going to be available on the OSIRIS-REx website, which is asteroidmission.org. And then data, as it becomes publicly available, is released to NASA's Planetary Data System. And that's where you can access all of the raw images that haven't undergone any processing. And that is available as a resource to the entire world to access the incredible data we've acquired with the OSIRIS-REx mission.
Absolutely. We've got one interesting question here. Was the impact to the asteroid so strong or strong enough to change its actual location?
The contact was imparted a very small force relative to the size of the asteroid. So the motion of the asteroid would be imperceptibly small. The spacecraft is the mass of a fan of a SUV, and touched it briefly, and the asteroid is the size of a hill. So dropping a car on the hill is not going to move the hill. So no.
All right, good to know. Okay, this is a great name. Out of Cheese on Periscope asks, what do you hope to actually learn from this sample collection? What are the implications?
Oh, I'd like to take this. So I'm on the sample analysis team, and this is what I've been waiting for, is to look at the samples. So we have over 50 hypotheses we want to test. Many of them involve understanding and verifying the observations we've made on the asteroid. I'm personally interested in the origin of organic compounds in the early solar system that maybe contributed to origin of life. And so looking at the ancient chemistry, like the amino acids, their chirality, their left versus right-handedness, so many questions, we need hours to discuss it. In fact, we have weekly meetings where we discuss it for hours.
It sounds like big questions and really big implications too. So
that's why we're here.
Ion, yes, absolutely. And we're so glad that you're doing this work. Ion on YouTube asks, how fast was the spacecraft going to collect the sample? And how can we guarantee we got a good sample that can actually give us data?
I'll take that one. We are just getting our telemetry back from the TAG event. We had a high gain pass over last night and through this morning. We've got just a treasure trove of data that we're digging through now to understand the spacecraft performance. One of those pieces of data is the contact velocity. And we came down right around our expected 10 centimeters per second. And for reference, walking speed is about 15 times faster than 10 centimeters per second. So we really were coming down at a very, very gentle, slow pace, and that was on purpose. And then in terms of how much material we collected and how well we know that, the official mission process for estimating the sample mass is going to happen later this week, actually on Saturday. And it's the sample mass measurement technique that we discussed a little bit before. And that's where the spacecraft stretches out its arm and spins slowly around. And it does that after TAG. We did that once before TAG as well, where we didn't have any sample inside the TAG-SAM device. And we'll do it again after TAG with sample in the TAG-SAM device. And the difference in the measurement between those two spins should give us information about how much mass we actually collected. We have other indirect techniques for evaluating how much sample we might have collected. In particular, using the SAMCAM, which is the same image or the same camera that we use to collect the images of the tag event itself, we can reorient the TAG-SAM head to actually be facing with the bottom into the field of view of the SAMCAM. So we can look directly into the TAG-SAM device itself, and we hope to have direct measurement of the material inside TAG-SAM by virtue of looking inside it. But that can only show us some, just because of limitations of the geometry. We can't see the entire collection volume inside the TAG-SAM device itself. So while that will give us some information, it's not the most accurate measurement. So we really are waiting for the sample mass measurement on Saturday.
Whew, Saturday seems like such a long time from now. Okay, moving right along, we've got so many questions. Thank you all for submitting your questions. Sam on Facebook asks, how fast would the material be ejected, and is that capable of damaging OSIRIS-REx at all? So I guess maybe, when the material was impacted, could that actually damage our little spacecraft?
I'll take that one again. I actually led up a study to address that very specific question, because we knew that was a possibility when we were designing the mission. So we actually did a very exhaustive study to look at the speeds and masses of material that we might pick off the surface. And the short answer is no, we don't feel like there's any risk to the spacecraft at all. Otherwise, we would have chosen a different technique to collect the sample. So there are some speeds of potentially 10 meters per second or 15 meters per second of material coming off the surface. But that is not fast enough to damage any of the equipment on board the spacecraft.
Well, thank goodness for that. All right, Amy from Facebook asks, is there any analytical data sent back to Earth regarding the sample, or do we really have to wait till 2023?
You really have to wait. Part of designing a mission is you need to design for what you require. And so it would be fun to add a whole bunch of instruments to interrogate the sample to give us a quick look. That would be not as good as what we have on the Earth, which is the whole reason we're bringing it back. But that costs a lot of money and costs a lot of time and space and mass. And it's better to invest that time in having the fantastic camera and spectrometer and LiDAR suite that took the data we can compare with the sample when we get back on Earth, and having the talented team to be able to solve these problems that we had on board, and that Bennu literally threw at us.
Yeah, can I add to that, Lauren?
Yes, of course, please.
Yeah, I think, so Jason is right. We won't be able to directly interrogate the sample using anything on board the spacecraft, but I think it's important to note that we gathered a lot of data of the sample site before we collected that sample. So we do have some great indications that where we gathered a sample from on Bennu is relatively young. It looks like it has a color that's reddish, and that might indicate a more recent exposure age. And there was also evidence of the presence of organic molecules and carbonates around the sample site. So we believe it will have some carbon-bearing material. So while that isn't, data directly taken of the sample itself, it gives us, it allows us to make some inferences about what the sample will look like, and they are all very promising.
Oh, love to hear it. That sounds great. And that is all the time we have for today. Thank you so much for joining us, Danny, Jason, and Bo. We know you're busy, and we've loved having you.
Thanks, Lauren.
Thank you.
Thank you. Great to be here.
And thank you for joining us at home. We've loved having you too. For more updates on OSIRIS-REx journey back to Earth, visit nasa.gov/OSIRIS-REx or follow @OSIRIS-REx on Twitter, Facebook, and Instagram. Check back with us in the first week of November when we hope to make an announcement, especially regarding whether or not sufficient sample was collected. So that's very exciting. Check that out. Be sure to check that out. Until next time, I'm Lauren Ward. Thanks again for joining us, and this has been NASA Science Live.